Can a moon vanish? It turns out it is possible. In the early days of astronomy, Zatnian moon Apotus routinely appeared to vanish from sight entirely. Some days it was there, and the next it was gone. This was the ultimate magician's trick. But as we figured out how it was done, Apotus's mysteries only grew deeper. That is because Apotus is a place of profound contrast. One half is plunged into near absolute darkness, while the other gleams with the brilliance of reflective ice. Around its equator, a colossal mountain range, an enormous stony girdle, wraps precisely around the moon like a belt forged by cosmic forces. It's one of the most enigmatic celestial bodies we've ever observed. Our story begins with astronomers who, bewildered by its unpredictable appearances, thought perhaps they had discovered a moon that defied the basic laws of visibility. Sometimes it was visible through the telescope, and then, inexplicably, it would disappear again. Yet this wasn't a trick of the instruments, nor an illusion of human error. From certain angles and under specific light conditions, Apotus would quite literally blend into the dark backdrop of space. Its dark hemisphere absorbs nearly all incoming light, rendering it practically invisible. Meanwhile, the bright side shines like a beacon, causing the moon to behave like a cosmic vanishing act. Modern imaging revealed that the surface is split so drastically that it looks like two entirely different moons stitched together. This bizarre contrast is what creates the optical illusion. The disappearance wasn't magical, it was scientific. But how did such a world form? What cosmic forces shaped such perfect symmetry and opposition? Was Apotus always like this? Or did something dramatic in its past sculpt it into this yin-yang shape? In the next segment, we'll journey deeper into Apotus geology, its icy cliffs, and the gravity dynamics that hold this delicate balance in place. This vanishing moon isn't just a spectacle. It's a key to understanding alien worlds with extreme conditions and deceptive appearances. Stay tuned. Apotus is a world quite literally split down the middle. So sharply defined is the boundary between light and dark that astronomers were initially puzzled whether they were observing one moon or two. One hemisphere dazzles with the reflection of sunlight off its icy surface, while the other lies cloaked in utter darkness, absorbing nearly all incoming radiation like a celestial black hole. This phenomenon is known as albedo dichotomy, an extreme contrast in reflectivity between two surfaces. On Apotus, this contrast is so intense that when viewed from certain angles, one half seems to vanish completely, blending into the void of space. The divide isn't just visual, it's geological. The bright side is covered in frozen nitrogen and water ice, giving it a mirror-like appearance. The dark side, by contrast, is coated with porous, carbon-rich material, likely the result of centuries of micrometeorite bombardment or space weathering. It's like looking at a single object, but seeing two entirely different moons. What caused such a division? Some scientists speculate that Apotus once collided with another moonlet, an impact that blasted one hemisphere with molten material while preserving the frozen nature of the other. Others believe it could be the result of tidal locking, or where one face of a moon is always turned toward its planet, receiving more light and warmth, while the other remains in eternal darkness. Either way, this split personality has turned Apotus into a celestial paradox. It doesn't just challenge our understanding of moons, it forces us to redefine what surface stability means in the vacuum of space. From a distance, the massive equatorial mountain range adds another layer to the mystery. This stone belt may have formed during the cooling process post-impact, or as tectonic forces attempted to equalize the gravitational distortions caused by its dual nature. In the next segment, we'll dive deeper into how Apotus may be a window into world-moon evolution across exoplanetary systems. What happens when similar conditions arise elsewhere in the cosmos? Could split moons be more common than we think? Apotus is just the beginning. Apotus may be one of the clearest windows we have into the science of moon formation. Its starkly split appearance, dramatic surface features, and orbiting behavior hint at a violent and complex origin. Scientists have proposed several theories for how moons like Apotus could come into existence. One widely accepted model is giant impact theory, where a massive object collides with a planet or protoplanet, ejecting debris into orbit. Over time, this debris coalesces, cools, and forms a moon. In Apotus' case, the possibility of such an impact is supported by its physical asymmetry. One hemisphere, the dark, scarred side, shows signs of intense bombardment and geological trauma. The bright side appears relatively pristine, as if it had formed from the outer layer of a different frozen body. Could Apotus be a hybrid of two celestial objects? Another theory involves gravitational capture. In this model, a passing object gets caught in a planet's gravitational field and becomes a moon. If Apotus originated from a distant region rich in ices and organics, that could explain its reflective side. The dark side may have been altered by space weathering after being pulled into orbit. Then there's co-formation theory, where a moon forms alongside its planet from the same disk of dust and gas. This is common for gas giants and their regular moons. However, Apotus's odd duality makes this explanation less likely, unless dramatic changes occurred later due to tidal heating or radiation damage. Whichever theory is true, Apotus provides an exceptional test case. Its mountain belt could be the scar of a massive merger. Its rotation may have been altered post-formation, and the split in albedo suggests different materials and temperatures during its birth. Adding complexity is the fact that Apotus exists in a region of space where solar radiation is intense. Cosmic rays may have stripped away volatile compounds from one hemisphere while leaving the other intact. This uneven radiation exposure would further exaggerate the moon's already divided identity. These factors, impacts, gravitational dynamics, radiation, and material composition, all combine to tell the tale of a moon that formed under extreme conditions. It's a narrative not just about one celestial body, but about the millions of moons that could exist across the universe. With the help of next-generation space telescopes and lunar probes, we are beginning to see these worlds not just as satellites, but as historical archives of cosmic violence, stability, and evolution. In Segment 4, we'll examine how Apotus compares to other moons, our own included, and what secrets might be hidden beneath its surface. Could this moon harbor subsurface oceans or volcanic remnants? Could it hint at past habitability? The deeper we look, the stranger it gets. As we continue to peel back the layers of Apotus, one question emerges louder than the rest. Could there be something beneath its icy surface? More specifically, could Apotus harbor a hidden ocean? The idea may sound far-fetched at first, but it's not without precedent. Several moons in our own solar system, like Europa, Enceladus, and Ganymede, are now believed to contain liquid oceans beneath layers of ice. These moons, despite being far from the Sun, may maintain internal heat through tidal flexing, allowing water to remain in a liquid state. Apotus shows signs that suggest a similar structure. Radar reflections observed in recent scans reveal slight distortions beneath its bright hemisphere, distortions that could indicate a layer of briny liquid between the icy crust and a rocky mantle. If true, this would place Apotus among a growing list of ocean worlds. The presence of a subsurface ocean would radically change how we view this moon. It wouldn't just be a visual illusion or a geologic anomaly. It could be a potential habitat. Life, after all, thrives in Earth's oceans even in the most extreme conditions. Deep-sea hydrothermal vents, acidic brine pools, even under thick polar ice. Could similar microbial life exist on Apotus? Supporting this hypothesis are thermal readings that show anomalous heat patterns along the equator, precisely where the mountainous belt lies. Scientists theorize that this region may contain fissures or weak points where heat escapes from the core, potentially providing the energy needed to sustain liquid water below. What about the dark side of the Moon? The low albedo and heavy carbon presence could suggest organic-rich material, possibly deposited from comets or created through radiation processing of ices. These compounds are essential for life as we know it. Of course, confirming the existence of a subsurface ocean would require an orbiter mission or a lander equipped with radar, spectrometers, and heat sensors. But if Apotus proves to be an ocean world, it will become a prime target in the search for extraterrestrial life. Even without life, Apotus offers a fascinating case of planetary evolution. An internal ocean would indicate past volcanic or tectonic activity, perhaps even ongoing hydrothermal circulation. These processes could sculpt the Moon's surface in subtle ways we're only beginning to interpret from a distance. And beyond Apotus lies a broader truth. If one moon can hide a secret ocean, others can too. Apotus could be the key to unlocking how common water might be on alien moons and how life might arise in the most unexpected places. In the next segment, we'll compare Apotus to Earth's moon and investigate the lessons our own satellite can teach us about what lies beneath otherworldly surfaces. The journey continues, and the mysteries only deepen. Apotus is undeniably strange, but just how different is it from our own moon? At first glance, Earth's moon and Apotus share some basic similarities. Both are natural satellites orbiting their parent bodies, both are roughly spherical in shape, and both have been shaped by eons of impacts and radiation. But that's where the similarities end. Earth's moon is coated with a relatively uniform regolith, or dusty rock layer, created over billions of years by micrometeorite impacts. Its surface is characterized by dark basaltic plains, maria, and brighter highlands, all exposed under constant sunlight and shadow due to its synchronous rotation. Apotus, on the other hand, presents a dualistic identity. One hemisphere gleams with ice and highly reflective materials, while the other is veiled in darkness, absorbing nearly all light that strikes it. This extreme albedo contrast creates the illusion of disappearance and gives Apotus its reputation as the vanishing moon. Moreover, the mountain belt that wraps around Apotus has no equivalent on Earth's moon. While Earth's moon has mountain ranges, they are fragmented and often formed from ancient impacts. Apotus's equatorial range seems almost symmetrical, like a seam stitched by nature, possibly caused by internal tectonic stress or remnants of a dramatic collision. The internal structures may also be radically different. Earth's moon has a small, partially molten core and no confirmed subsurface ocean. In contrast, recent thermal and radar data suggest that Apotus may have a hidden briny ocean beneath its icy crust. This opens the door to biological potential and geochemical processes completely absent on our moon. Then there's the question of origin. Earth's moon is widely accepted to have formed from a giant impact between Earth and a Mars-sized object, creating a debris disk that coalesced into the satellite we know. Apotus, however, defies singular classification. Theories range from gravitational capture to hybrid co-formation, and even the possibility of it being the fused remains of two separate moons. When comparing orbits, our moon is relatively stable, maintaining a near-circular path around Earth. Apotus, however, shows signs of an orbital wobble, a slight oscillation that may result from uneven mass distribution between its two halves or gravitational perturbations from nearby celestial bodies. This wobble contributes to how and when the moon appears to vanish from certain observational angles. The biggest difference may be psychological. Earth's moon is familiar, comforting, a constant in our night sky. Apotus is an enigma, a celestial trickster. Its behavior forces us to rethink what we define as a moon. It reminds us that the universe is still full of surprises, and that even basic assumptions, like visibility, can be challenged by nature. As we continue to study moons across the solar system and beyond, we may begin to understand Apotus not as an exception, but as a new category of moon altogether. The kind shaped by extremes, rich in contrast, and forged in conditions we're only starting to imagine. In the next segment, we'll explore what missions could reveal more about Apotus. What kind of spacecraft would we need? What instruments could peer beneath its ice and uncover its secrets? The answers may shape the next era of lunar exploration. If we ever hope to truly understand Apotus, the vanishing moon, we'll need to go there. Observation from afar has given us tantalizing clues, but direct exploration would unlock the secrets hidden beneath its icy skin and shrouded dark hemisphere. But how would such a mission work? First, we'd need an orbiter, a spacecraft capable of entering stable orbit around Apotus. Because of its unusual surface reflectivity and possible orbital wobble, this orbiter would need advanced imaging systems capable of adapting to low-light conditions on the dark side and managing intense glare on the icy side. A dual sensor system combining thermal and radar vision would help map both hemispheres in detail. Once a high-resolution surface map is compiled, the next phase would involve a robotic lander. Landing on Apotus presents unique challenges. The bright hemisphere may have slippery, reflective ice, while the dark side could contain jagged, carbon-rich formations. The lander must have adaptive landing gear and automated navigation to react in real time to surface irregularities. A drilling system would be key. To confirm the existence of a Apotus subsurface ocean, a thermal drill would be designed to penetrate the icy crust. Samples extracted from beneath the surface could be analyzed for organic compounds, salts, and signs of hydrothermal activity, key indicators for habitability. Communication is another hurdle. Since one hemisphere of Apotus absorbs nearly all electromagnetic radiation, maintaining constant data transmission would require either a relay satellite sent in orbit or multiple landers positioned across different terrain zones. Power would likely be supplied via compact bund nuclear batteries, as solar panels would be ineffective on the dark side. A more ambitious version of the mission might include a penetrator probe, a projectile device that slams into the surface and transmits seismic data. This would allow scientists to build a model of the moon's internal structure, helping determine whether a liquid ocean truly exists and how thick the outer shell is. Over time, a long-term observation platform could monitor for geological activity, such as ice cracking, minor tremors, or thermal hotspots that would indicate internal heating and potential subsurface movement. And what about crewed missions? At present, the conditions on Apotus are too extreme for humans. Temperatures on the dark side likely drop to near absolute zero, and its low gravity makes landing and movement hazardous. However, robotic missions could pave the way for future generations of scientists to visit orbit, perhaps aboard a mothership stationed nearby for close observation. The mission to Apotus would not be just a technical milestone. It would be a philosophical one. Exploring this moon would challenge our assumptions about what moons are, what conditions they can survive in, and what possibilities they hold. And there's another angle to consider. What if Apotus is not unique? A successful mission could serve as a blueprint for exploring hundreds of other moons with similar characteristics scattered across the galaxy. It could even inform future missions to icy exoplanets or rogue objects wandering the void. In Segment 7, we'll explore what Apotus can teach us about young planetary systems beyond our own, how studying this single moon may give us insight into the formation and diversity of entire solar systems. Because in space, every answer leads to bigger questions. Studying a single moon like Apotus might seem like a small step in space exploration. But what if that small step gave us insight into the entire architecture of alien solar systems? As our tools for detecting exoplanets improve, scientists are turning their attention not just to the planets themselves, but to the moons that orbit them. These alien moons, called exomoons, could outnumber planets by the thousands and may hold the same, if not greater, potential for habitability. What makes moons like Apotus especially valuable is how their extreme diversity challenges traditional models of planetary formation. Most early models assumed moons were relatively simple, formed from leftover material or captured by gravity. But Apotus, with its dual hemispheres, subsurface ocean, equatorial ridge, and vanishing effect, tells a different story. Moons can be just as complex, volatile, and diverse as planets themselves. If Apotus exists in our stellar neighborhood, what stranger moons might orbit distant gas giants in other star systems? Could some have atmospheres? Could they host alien oceans, tectonic activity, or even life? Exoplanet hunting missions like Kepler and TESS have already discovered thousands of exoplanets. But finding their moons is more difficult due to their smaller size and limited gravitational effects. However, new instruments such as the James Webb Space Telescope, JWST, and the upcoming Plato and LUVOIR missions may soon provide us with the precision needed to detect large exomoons and even analyze their compositions. Apotus serves as a model. By analyzing how it interacts with light, gravity, and its environment, we can calibrate our instruments to recognize similar anomalies in other star systems. The way Apotus vanishes from view due to albedo contrast could help us interpret similar dips in brightness from distant moons. Additionally, the presence of subsurface oceans on moons like Apotus opens up a revolutionary idea that life may not require a planet at all. A moon with internal heat, water, and organic materials could become a cradle of biology, especially if it's orbiting a stable gas giant within the habitable zone. Some scientists now suggest that exomoons may be more likely to support life than exoplanets due to their ability to retain heat from tidal forces and their potential for chemical cycling. If Apotus has taught us anything, it's that complexity doesn't require size. It requires the right conditions. What's more, moons might survive events that destroy planets. If a planet is scorched by its star or ejected from its orbit, its moons might linger in space, frozen time capsules of pre-catastrophe conditions. The rogue moons could become vital to understanding long-lost planetary histories. Through the lens of Apotus, we begin to see moons not as accessories, but as key players in the cosmic game of habitability, evolution, and survival. In the next segment, we'll zoom out even further. How does Apotus and moons like it reshape humanity's quest for meaning in the universe? What does it say about our place among the stars? The journey is far from over. Stay with us. From the moment humanity first looked up at the night sky, we've asked the question, are we alone? For decades, that question centered on planets: Mars, Europa, Kepler 452b. We've scanned atmospheres, searched for biosignatures, and imagined distant Earths circling distant stars. But what if the real answer isn't found on a planet, but on a moon? Apotus brings this possibility to the forefront. Its frozen surface, mysterious equatorial ridge, and possible subsurface ocean hint at conditions far stranger and more potentially life-sustaining than many exoplanets we've discovered so far. We've long known that life can adapt to extremes. Microorganisms on Earth live near volcanic vents at the ocean floor, inside Antarctic ice, even within nuclear reactors. So if Apotus has internal heating, liquid water, and the right mix of carbon compounds, it could host life forms adapted to total darkness and isolation. And if Apotus is just one of many such moons, imagine the scale. Every gas giant discovered outside our solar system may have multiple moons. Statistically, that could mean billions of moons across the galaxy, each a potential habitat. But Apotus reveals more than biology. It reflects something fundamental about human nature, our search for meaning, for connection, for understanding of the universe and our place within it. The idea that moons could host life forces us to reconsider what we think is normal. Earth is not the center. Planets may not even be the rule. It also reframes the famous Fermi paradox. If intelligent life is common, where is everyone? Perhaps we've been looking in the wrong places. Maybe advanced civilizations evolved under ice, in oceans shielded from radiation, never needing a surface or sunlight. Could life on Apotus-like moons be so different that we fail to recognize it when we see it? Would their biology even use the same molecules? Or would we need to invent new tools and new thinking to detect them? The deeper implication is spiritual as well as scientific. If Apotus holds life, or even just the conditions for life, it expands our concept of what it means to exist in this universe. It tells us that life is not confined to blue skies and green forests, but may emerge wherever nature allows complexity to rise from chaos. And for those who wonder why space exploration matters, Apotus provides the answer because it forces us to confront the unknown. It invites humility, it demands curiosity, and it rewards us with a deeper sense of belonging to a universe far more diverse, mysterious, and alive than we ever imagined. In the next segment, we'll conclude our journey with a powerful reflection on what Apotus teaches us about cosmic perspective and how even a single moon can shift the trajectory of human thought. Stay with us for the final chapter. Apotus began as a curiosity, a vanishing object in the night sky. But now, having followed its mystery through light, shadow, geology, and possibility, we arrive at something deeper: perspective. This final chapter is not about facts and figures. It's about what a single moon, floating in a distant system, can teach us about being human. Apotus shows us the illusion of finality, that what we perceive is often shaped by where we're standing and when we're looking. Early astronomers believed Apotus disappeared, but it was never gone. It was simply hidden by light, angle, and shadow. How many other truths in the universe and in life are hidden in similar ways? The moon also challenges our assumptions about normalcy and rarity. It tells us that the universe is not uniform, that extremes are not exceptions, but expressions of the full cosmic palette. Moons like Apotus stretch our definitions, and in doing so, stretch our minds. There's also a lesson in humility. For centuries, humans believed the Earth was the center of everything. Then the sun, then the galaxy. With Apotus, we're reminded that even within moons, those quiet companions to planets, exist wonders far beyond our understanding. The cosmos doesn't revolve around us, but we are privileged to witness it. In many ways, Apotus mirrors humanity. It wears two faces, one bright and visible, one dark and hidden. It balances chaos with order, silence with motion. It is still and spinning, distant, yet deeply connected to everything around it. That's the essence of the cosmic perspective. Realizing that we are both insignificant in scale and profoundly significant in meaning. Because out of all the stars, all the galaxies, all the frozen moons and molten worlds, we are the ones asking questions. And that matters. Perhaps Apotus will never host a mission. Perhaps we'll never send a lander, drill into its crust, or confirm what lies beneath. But in observing it, modeling it, and imagining it, we have already expanded the boundaries of our consciousness. That is what space does best. Not just answer questions, but ignite better ones. What else is out there? How many more Apotus-like moons are waiting to be seen? And how many mysteries lie within them? Not just scientific, but philosophical. The search for life, for understanding, for truth, is a search that starts with a telescope, but always ends in the soul. So as we close this series, let us not forget, Apotus is more than a moon. It's a mirror, a symbol of cosmic contrast, but also of human clarity. From the icy silence of deep space, it reflects a single truth. The universe is not empty. It is full of questions, of possibilities, of wonder. Thank you for joining us on this journey. This is Bo Infinity Beyond, where we don't just explore space, we explore meaning.